Good afternoon, everyone. Thank you very much for joining us in this webinar. We are in the new normal now. So originally, the WOHUB Distinguished Lectures was set up 2 years ago, and it was actually a face-to-face kind of presentation. But under the new situation, we have to change. And so we thought that a webinar kind of session is worth trying to see whether it's effective. And this is our first session that is conducted using Zoom. And I hope that you can bear with us if there's any teething problem. So today we are very fortunate to have our distinguished WOHUB Distinguished Speaker, Honorary Fellow, Professor Tam, to share with us his vast experience in the field of concrete technology. And I thought that it's good also to introduce our new staff who are working in a similar area, but in a newer direction. And so I have invited Dr. Tu Hongjian to share with us his work on concrete research, especially in 3D printing, and Dr. Geng Guo Chiang, who is working on concrete materials technology. He's actually first degree is actually materials science and engineering, but his PhD is actually in civil engineering on concrete technology. So I thought that it was good for us to share with you the kind of research work that NUS is doing at this point in time. So, why this topic? The reason for choosing concrete is partly because of the expertise of these three speakers, especially Prof. Tam. But I think that concrete is a very important material to us, and of concern is actually sustainability, durability, safety, and productivity. And that's what this series, this talk is going to focus on. And of course, we will actually try to link research with practice. So I hope that you will actually gain useful knowledge after this webinar. So I should not take much time further, except to say that Prof. Tam is now he has retired and he's now Honorary Fellow in recognition of his many years of contributions to NUS and to the industry. And we are very glad that Prof. Tam has continuously come in to the university to help us interact with staff and students. So he's very well known, and so I don't want to spend too much time introducing him. Dr. Tu actually obtained his PhD from NUS after graduating from I think Shanghai Jiao Tong University, and he has actually been a research fellow for many years before joining Swinburne University in Melbourne, and then returned to join us. Dr. Geng actually got his bachelor's from Southeast University, and actually his PhD is from UC Berkeley before he went to Switzerland to do his postdoc and then join us as an assistant professor. So now I would like to invite Prof. Tam to actually kick off this lecture. Prof. Tam, please.
Thank you, Prof. Quack, for introducing us. And I'm particularly happy that I had the opportunity to speak in this series of lectures. Today, I'm going to talk about something that links engineering to practice. So my intention is to talk about how we can improve our standard test method to bring it into something more useful to reflect what we want in practice. So this was presented last year as a much bigger lecture at our World in Concrete, but today I'm going to select two of the topics to go a little bit more detail because of limitation of time. Now, this concept of going into to do with performance rather than just prescriptive or design standards, which is common, although the standard conformity testing of materials is necessary, but unfortunately it's not sufficient to avoid problems during the actual construction practice. So today I'm trying to see what we can do with standard tests to modify it and extend it to get some useful information that the practitioners can actually apply. Now, standard tests are intended to go and look into the assessing the technical requirements, which are usually in a contract specification. In order to compare results from different test labs and so on, the equipment, procedure, as well as many details on how to prepare the specimen, how to test, and the environment and so on are highly prescriptive. Now, in order so that we all can reproduce similar results using similar material. Unfortunately, not all of those conditions that we impose on the standard test are the ones we have in practice. So one of the things that I learned very early is that we keep following the European practice of testing everything at 20 degrees Celsius, whereas in our environment, concrete always at around 30 degrees in practice. So that got me thinking about how the tropical environment need us to adjust the way we work in concrete technology, basing on science and understanding of the technology. So today I've selected two topics. First thing, something many of us are interested in, self-compacting concrete. And one of the difficulties is how well can they pass reinforcement bars and flow around them and fill up all the space within the formwork. The next one I'm talking about is something to do with co-joint. In thick sections, we often have delay in casting different layers. As a result, the concrete could have partially set due to unfortunate delay, due to traffic, breakdown of equipment, or whatever other reason, or even in our local climate, suddenly heavy downpour. And that means somebody had to decide what to do at the end of the event, how we should continue. I know in practice, contractors always continue, and then we have to sort out the issues afterwards. But can we find a better way to decide what we could do? So that was the other second objective. Now this is what we call the passing ability. The word J-ring, probably because it was decided by a Japanese professor. So the J probably stands for Japan. So in this particular test, which is accepted under the EN, we have a cone of concrete placed inside the ring. We pull up the slump cone and let it flow. Some of the concrete will flow past the bars, and we have to compare the little gap in the here between the top of the pile and the ring and what is on the outside. What is the concrete on the outside here in the blue circle. And the difference is what we judge to be the ability for the concrete to go past the reinforcement bars. So you can have two types of rings. There are 12 bars with 18 mm. That gives us a clear gap between the bars of 59 mm. And when we have 16 bars of the same diameter, then it becomes 40. So it's between 40 nominal clear spacing and 60, which is quite common in our practice. Now, the other one is when the concrete flow until it reaches 500 diameter. The ring at most is 300. When it reaches 500, the time taken will be another measure of how well the concrete can flow. Now, the passing ability of self-compacting concrete in the US, they like to call it self-consolidating concrete, using the J-ring. Both in ASTM and EN, we use the same ring, but we don't treat the result the same way. In the EN standard, we call it the J-ring step. That means the change in height between the one in the middle and the concrete, the coke flow past the ring. This is the J-ring, and you're supposed to be less than 10 mm. But if you look at the actual height of those concrete, it's very close to that. So the values in terms of repeatability and reproducibility are given in an example, about 5 to 6 in repeatability, and reproducibility 7 to 8. That means if you do the test twice, it can differ by 5 to 6 mm, and you are controlling it to less than 10. So that means there's a lot of uncertainties in the test result. So it is not really the best test method. Now, in the ASTM, they chose an alternate method of doing it, which actually was pioneered by us in NUS. We look at the flow diameter rather than the height. That means the flow without the ring and the flow with the ring. And we call that a passing index. Now in ASTM, for practice, that is too detailed. In research, it's very good. We'll show you later. But in practice, they want a simple rule. So they use 25 mm difference in the flow diameter. That means the flow of the concrete is reduced by 25 mm from the standard slump flow. Then it's considered okay. Between 25 and 50, not too good. Over 50, definitely not acceptable. So that is a very good simple site practice. But for us, we can extend it to a little bit more, and by using the index, which I'm going to explain further, that will particularly give us a lot of other things we can do. Now, so this was first published by one of our final year project students, and another one subsequently do a fair bit more work on this. So the passing ability index, oh sorry, should be PAI, not PAS, is the P-ring flow diameter and the slump flow. Now we call it the P-ring because we wanted to make the ring bigger. Instead of 300 mm, we increase it to 500 mm, and we'll explain why we do that, because that will give us a lot more information, flexibility in carrying out the test to meet what is site requirement. Now, so this is the slump cone. This is the J-ring, 300 mm. This is our NUS design P-ring. We call it P for passing ability. My student was suggesting maybe you should follow J-ring and call it an S-ring. I said better not. So I think we just call it the P-ring, passing ability ring, 500. Now this particular set of equipment was duplicated by our final year project student, who is now a director in one of his own concrete RMC in Sabah. So you can see he's a very keen person and apply what he has learned from the university to the practice. Now, so in order to do the test comparatively in research, you need 3 helpers to do all the 3 tests simultaneously. We all know the flowing ability of concrete changes with time. So in the research, he was all by himself. He had to do one after the other, and he complained to me that it's not fair. He doesn't know which way is the best sequence, ABC or BAC, BA, and so on. And it will make a slight difference. So in his own study, he actually got 3 workers to do it simultaneously. And he also used Teflon bars instead of reinforcement bar because he doesn't want to have any friction. Because you might even argue whether the deformed bar, where are the ribs, where are the pips, that will also change the behavior. So you can see in research, we are trying to be a little bit more refined. Now, strictly speaking, we are not only talking about the gap, we are talking about the number of bars in a given area blocking the flow of concrete. So there are two ideas. So if you look back and look at Astm, they're talking about blockage assessment. Now that got me thinking that we should be thinking about the blocking ratio. That means in a particular cross-section, how many bars are there in terms of the width of the section, and then there would be amount of blockage. So in a ring, it will be the number of bars around the ring, and so on. So this is what we did. So in our test, we added the additional idea of including the blockage as another parameter. So it relates to both the flowing change in diameter, the clear gap spacing, as well as the degree of blockage. So with the J ring is fixed. So we have only two combinations of number of bars, and hence the clear spacing and the blockage is fixed, only two variations. With the P ring, we no longer fix the bars. The bars are put on, and we can change the number of bars by omitting some of them, and so on. And using different diameter of bars, they're giving us an opportunity to best simulate what is the project we have. We have something very simple that might be only 20, 30 mm bars to very big ones like 40 mm, like in a rough foundation, they are only 100 mm apart. So if you look at the table, which is what they have, the J ring, the narrow gap, the wide gap, 40 and 60 nominal. The blockage is there. Oh, somehow I cannot get rid of this. It's blocking my view. So whereas in the P ring, I can simulate that, but I cannot simulate both the gap and the blockage exactly. Now, so that means what we can do is to compare with the J ring to get an understanding of what they have been doing, link back to practice and our experience, and yet we can now start to change the combination. Why is the clear gap of 40 and 60 selected in the J ring? It goes all the way back to the earlier test, the L box. The L box have exactly the same thing. The gap of 41 mm and 59 mm, just like the two J rings. But then they have either 2 or 3 12 mm diameter bars and not the 18 mm bars. And the distance here is 200 mm. So it has also a different blockage ratio. So you can see a lot of our so-called standardized testing are semi-empirical and do not always cater for all the needs in real practice. So that's why we start to develop the P ring to enable us to do that. Now, so the width of the box is only 200, ended up with a blocking ratio of 12% and 18% of the cross-section, against more like 23 and 32 in the J ring. So we do not think that the two tests are actually directly linkable. So they are separate tests having separate interpretation. I wonder what happens if he passes one and fails the other. The engineers have a big headache trying to decide which one to say is the controlling test. Table 3 is what we have turned up to produce later on to show what happened. With a P ring with 500 mm diameter, we have 24 equally spaced bars. We can provide different combination of clear spacing as well as blocking ratio. Let me take an example of a very common one, rough foundation, 40 mm bars at 100 mm centers. So you can see the clear space between the bars are only 60 mm, And the blocking ratio out of the 100, 40% is blocked. Now this is clear gap. So what can we simulate? I cannot simulate exactly equal to that, but simulate to something close to it, 58 and 41. Now, on the other hand, we have the clear gap of 51, a blocking ratio in the J ring, which is so different and from the practice. So we are now trying to see what we can do. Now, if we start to repeat the P ring test over a period of time since batching during our initial testing stage, we can notice with time what is the change in our passing ability index. That will tell us, is there a limit of the change from beyond which we should stop concreting and treat it as a cold joint. Now, in the J-ring method and the L-box, we have no such way to make a choice. So we hope the new method will enable us to do something more, even on the job site. So you can see now, oops, sorry. I can assimilate that with very big diameter bar. To get the 60 and 40, I can use 8 number of 70 mm bars. That will give me close to 56 and 36. But if I use 16, 14 mm, 40 mm bars, I get 58 and 61, even better. But of course, then I have to use a slightly different ring so that the number of bars that I can put around the circumference is slightly different. So instead of the wide gap and narrow gap, we have now two type A and type B P rings. So here is a table telling us what we can do. I won't go into it in detail, but you can see the difference between the same 500 mm diameter, but only the different arrangement of the number of bars that we can put in, type A and type B. So the passing ability index is the flow diameter with the P ring as against the flow diameter of the standard slump flow test. How much we have lost. So that is a ratio. Now this ratio then can be diminishing with time, and we have now have a control, not only go, no go, but actually decide for ourselves what is a practical limiting limit that we really cannot tolerate. Because in practice, there's always a degree of tolerance that we want to apply. So you can see that by digging into this account, I can do that and give you an example of one of the tests. Here, the number of clear spacing. Here is the slump flow. So you can see for both rings added together, producing all these experimental points. And of course, the fit is still not the best, but it's still not too bad if you look at it from that point of view. So what we want to look at is try and use how we can do the P ring to do a better test. If you compare it with the J ring, you can obviously see the difference. I will not go into details, but you can see that the paper that we publish in will give you a lot more numbers and details. But just to show you what a typical result look like. Now, in comparison, you can see 300 to 500. So the time taken for the slump to flow after you lift up the slump cone to reach 300 is much, much shorter than to reach 500. In effect, the time to reach 300 is so short. ASTM say don't even use it because it's so uncertain. We are talking about 3 to 5 seconds. You have to be very fast with your stopwatch. And of course, sometimes the flow is not completely circular. So what do you take? The first point to reach the circle, or the average, or the last point? So it is so fast, you cannot do it. With 500, the speed is slowed down. That means we are now able to look at the time taken to flow from the 200 slump cone to 500. A bit longer time so that the number of seconds is increased and we have a better judgment of the actual thing in relation to the degree of uncertainty. So you can see, the passing ability of the fresh concrete over the J rate of the flow time, the T500 as they call it, is much longer compared to the T300 in the J ring. So you can see that the P ring has a lot more flexibility. Now, I have to throw a bit faster so that we can get on to the next topic. So basically, the advantage of the P ring is a bigger diameter, enable us to have more combination of actual bar spacing and blockage, and also enable us to test bigger aggregate. At the moment, if you got 40 mm aggregate, you have difficulty doing the J-ring test. P-ring also enable us to do the flow value of the T500 in lieu of the T300, and we also have the TF, that means the final time it stopped flowing. So all these are additional values that we can get if we start doing the P-ring. So now let me move on to the next topic. I hope I'm not going too slow. I tend to be slow in my talking. This is what we call the stiffening time of concrete. Now, of course, in practice, they call it the setting time. I do not like the term setting time because we have setting time of cement from which we make the same concrete. And yet the setting time of cement, setting time of concrete using the cement are completely different test method, different values, and they do not even have a direct linkage other than one better, the other one will be better. So basically, I would like to call it stiffening time because our concrete is stiffening, not setting. Setting is an hydration process that finally reach solid from a semi-liquid to a solid stage. Whereas stiffening means it is in the stage of a liquid transforming to a solid. So I call it stiffening time just to make a difference. Now, in the UK, the BS 5075 used to have this setting time test, which is slightly done in a different way from the original ASTM test, which I did numerical times for my PhD thesis. And so I know this test inside out. Unlike the setting time of cement, which uses a white cat needle. I wonder how many of our students still remember what the white cat needle looked like. But these days, we don't make them do the lab, so maybe they're not even familiar with the difference between the white cat needle and what we are doing in the setting time. Another thing that we can notice is because the original test used equipment based on soil test, which I'll come back to that, they cannot test with all the 20 mm aggregate. So the wet sift the mortar fraction and test. So that is further moving away from the real life, which is concrete. So we can see what is happening in the actual test. Now, so in the ASTM C403, initially they start using a handheld device, which is used by us to technical engineers for testing clay. And it has a force of 110 pounds or just about 500 newtons. So UK modified it, and they use a balance to put the specimen and then push the penetrator into it. So that gives us a little bit more flexibility. So let me show you. This is the original ASTM test equipment. Those of people in the soil mechanics will recognize this as a site tool for testing the penetration resistance for clay. Now, in the UK, they do not want to change the different sizes to cater for different penetration resistance. So they use only a single size. And they also are not interested in the upper end. So the first one, ASTM, 500 PSI, happened to be 3.5 MPa, is when the workabilities start to be very difficult to homogenize the concrete. This other one at 4,000 PSI is actually hardening. They're supposed in a cylinder to get you 100 PSI. So UK says that has no much interest for fresh concrete, but more interestingly, let's look at the lower end. At this one, in this particular one, it's only 0.5 MPa, and that is the time where our slump start to fall off rapidly. That means our slump retention start to decrease before we reach the 500 psi, which is called the initial setting time, and the other one is the final setting time. So now we have other equipment like this with a pressure gauge, with a proving ring, and of course today we can have transducers and a lot much better method of doing the force. But I still prefer that we should use a single probe so that the side friction, for soil mechanics people, you will know, in any cylinder that you push into a soil, not only you have the end friction, but you also have the side friction. This one will introduce very different combination. So stiffening time or the setting time is penetration resistant. So the initial setting time at 500 psi or 3.5 MPa is deemed to be critical. That might end up having a cold joint. Now this is a practical observation, or shall we say by choice on site, not because it has a particular meaning. I think our speaker later on will tell us more about how concrete stiffen, and you will understand this much better. Now, a real cold joint is a construction joint, and you can always see a black line. But however, in our actual practice, we don't always end up with a definite cold joint. So what we have now is, in practice, the new concrete that is placed over the delayed concrete of placing are now in the mix with a vibrator, which they always do on the job site. No matter how long is the delay, the subcontractor will never stop work because he has ordered all the concrete and he has to finish the job. Otherwise, he doesn't even know how to restart. So we always end up with a big issue on the job site. Many of those of us in practice will have, unfortunately, occasionally face this issue. So now what we actually created is not a cold joint, but a weakened zone. So this is of interest. If we have a method to decide what is the tolerance, because every time we design a concrete, there is always a safety margin to give us a lot more benefit than above the minimum that we require. So we need to make use of that side of decision making. So 3.5 is taken as it is. Okay, let's accept it for the time being until we have a better criteria. So let us see, is there a better approach, a more rational way of doing it than just 1 minute. Now, okay, so we started a study sometime back in the university, and we now try to look at the interface. We started off by casting a beam horizontally. Then after a while, the student asked me, but on the job site, our joint is horizontal, whereas our delay joint is vertical. So it doesn't make sense. So we use a beam because we can then use a fractional test. So okay, then we decided we did it not the best way. So we now design a vertical beam mold, 100 mm square, 400 mm long. The upper 200 will be cast later, and the lower 200 mm will have a face. That interface can be used to study what we can do with it. So after we remove the beam, after 1 day, then we cure it and then we test. Now this is our vertical mold that we make, quite expensive. And then this is the beam that we test in third point loading. You can see here. So the student had to check whether, because we are casting the beam vertically, are we sure we get a flat surface? So this ruler is there to look at the gap, look reasonable or not, before we do the actual fractional test. So let me show you the typical result. This is what happened. If we don't disturb the interface, or before I forget, this is the interface that we create. Now, so after 3 hours, we put the second level up. This interface can be disturbed or undisturbed. In the laboratory, the way we disturb it is using a rod to poke through 50 mm. We put another 100 mm concrete on top, push in, mixing with the next 50 mm and create a weak zone, and to do the same after 6 hours. So when we do that, this is now what happened to the test result. If we do not disturb the surface, it falls off very rapidly. Now that means this would be a situation if you are placing SCC. You don't even have a vibrator on job site, so obviously you don't disturb the interface. You just continue pouring concrete down. But if we disturb it in our method, you can notice a very small change. So if we are a bit more detailed, we can now ask ourselves, how much decrease can a practicing engineer tolerate on a job site, knowing that the concrete is of a higher grade to start off? So that means now we have a better means of making a more rational decision. So in a preliminary study, after we have done our mortar, wet sieve mortar, we decided, why can't we penetrate the concrete? There's nothing to prevent us that we cannot do a similar test with the concrete. So we did it. The same concrete, the wet sieve mortar at 3.5 MPa at that time, that particular mix of concrete showed us about 10 MPa. We did it a couple of times, always around about 10 MPa. So approximately when the wet sieve mortar is 3.5, which we have been taking as a criteria for co-joint, we can now transfer it to 10 MPa in the concrete. That means now it gives us a chance to actually test the concrete on the job site. Now, so if you do the result by using the log curve as recommended in ASTM, then you can see when the concrete reaches 3.5 MPa, this is the time, and at that time, the wet sieve mortar reached this, the concrete reached that, and that is 10 MPa. So now, with this particular concrete, we can use 10 MPa in lieu of the 3.5 in the wet sieve mortar as the criteria for co-joint. So that means now we have a way eventually to design a probe that can test our concrete by resting the equipment on top in a rough foundation, on top of the reinforcement bar on the top gauge, and push it down to whatever layer down below, 3-4 meters below, and test what is the penetration resistance of the concrete before we have add the next layer after a few hours of delay and avoided. So that gives us something very meaningful. So you can see now why we suggested this method, because we can now not only do that, we can start to look into remedial measures. What are these? Actually, our final year project students will be exploring this in the coming year. Can we add a slurry? Difficult? Can we put a bonding agent without disturbing, which is easier? But if we have to disturb, can we add a stronger grade concrete? What grade do we need to compensate for the loss? Now, all these are areas for our further studies. So I hope you all will look forward to more work and more results from us to help the industry. So in closing, I'd like to thank the people for helping me get this result, the students and my colleagues who are looking after the FYP, as well as for CI Premier for allowing me to make use of the same results that I presented at the conference last year. Thank you. I hope if you have any question, please do post them to me. If we don't have time because it's too long, send me an email and I can give you a more detailed answer. Thank you.
Okay, thank you, Prof. Tam. We'll leave the Q&A to after the third speaker. So now I would like to invite Dr. Tu Hongjian to make his presentation. Dr. Tu, please.
All right, I hope you can see my screen now. Thank you, Prof. Greg, for the kind invitation and the kind of introduction. It's my great pleasure to contribute to this seminar with Prof. Tam and Dr. Gung. So my talk will focus on digital fabrication of concrete by 3D printing. So here is the outline of this talk. I will first introduce digital fabrication and 3D concrete printing. After that, I will introduce a few major challenges facing this area. And then I will focus more on the solutions, what researchers are doing, including ourselves at the NUS. At the end of the presentation, I will introduce what facilities are available at our department for the research in this area. So concrete is the most widely used materials in the construction industry. I think many of you are familiar with this photo, the pouring of concrete at job site. This is a very heavy, highly labor-intensive industry. So in the past years, the digital fabrication started to emerge. Let's define digital fabrication first. Digital fabrication should be digitally modeling plus a computer-controlled production. So it has two parts, modeling and computer-controlled production. So from the photo on the left, it is a manually controlled production. While with the development of technology, I think now we can print buildings like the photo shown on the right. So you can see that there's almost no labor workers on the site. Okay. There are a few main motivations for the digital fabrication or 3D concrete printing. I want to say 3D concrete printing is one subset of digital fabrication. There are other types of digital fabrication. 3D concrete printing is additive manufacturing. So I will focus on 3D printing in this talk. One of the greatest motivation for 3D concrete printing is the low productivity for construction. The chart on the right shows some comparison between construction with other disciplines. You can see that in the past few decades, agriculture or other manufacturing, the productivities are increasing steadily. However, the construction industry, the productivity is maintaining at a low level or even decreasing. I think this is because the construction industry is slow to adopt new technology. And the second driving factor is the increasing labor cost. I think this is more obvious for Singapore, especially in the context of post-COVID-19 situation. There are other motivations, including the very high injury rate in construction. The 3D concrete printing, it's very good for the designers because it can realize the freedom for their design, even for complex shape. And also because by using 3D concrete printing, we can just put materials in those places we want. So we don't generate as much waste as the traditional construction method. So all these factors gave the construction industry great motivations on this 3D concrete printing. And concrete printing is not only in laboratory nowadays. Actually, there are some applications already. So 2 years ago, the world's first 3D printed bridge was in use in the Netherlands. The span is 8 meters. Later, I will talk about this in more details. And last year, in China, one university has rebuilt or reproduced a Zhaozhou bridge by 3D printing. And this bridge has a 20-meter span. It's very huge. And at the end of last year, GE was collaborating with Lafarge, one of the biggest concrete supplier in the world, to 3D print concrete base for wind turbine towers. This tower base has 10 meter high, so it's a very impressive progress in the industry. So this is the introductions for why people are using and how far they have go to the market. And now I'm going to introduce you a few main challenges, because this is a new area, so there are lots of very critical challenges. And this animation on the screen shows you a very typical layer by layer 3D printing concrete. And the first challenge is the weak interlayer bond. I think Prof. Tam just now have introduced the cold joint for different concrete lift. And 3D concrete printing has a lot of cold joints because the fabrication is layer by layer. The photo at the bottom is the CT scanning done by my student, and you can see the difference. This is the porosity, the microstructures at the interlayer at the bottom here, and the microstructure in the filament. So it's very obvious to note the interlayer has more porosity, and the pore size is much bigger than the filament. So the interlayer bond is something that can control the concrete quality, mechanical strength, and then the durability. There are other challenges, to name a few, to integrate reinforcement with the 3D printing concrete is something that many researchers are working on nowadays. If you see this photo or animation carefully, you will find actually the printing ink is something we call mortar or paste, because there's no coarse aggregate at all. So technically, this is not concrete. This is a mortar or cement paste. And the number 4 challenge is long-term performance. We are not very clear about the performance of printed concrete structures in the long term, because this technology has only emerged within a few years. And of course, there are some lack of standardization or specification for structural design. I will focus on the 4 main challenges in the next few slides. I will introduce you what the researchers are doing to mitigate these challenges or address those challenges. Let's start with the interlayer bond. There are a few ways, 2 main categories, mechanically and chemically. So one researcher from Germany is using robot to print concrete, and at the same time, he used a robot to insert a steel rebar. But the steel rebar is not continuous, it's just a short rebar to improve the interlayer performance. And the researchers investigated the way they insert the short fibers, including the direct insertion or screwing, or a combination with insertion with grouting. So he have investigated the interface between the rebar and the matrix. So they gave a very good result, showing the interfacial performance has been greatly improved. And similarly, some researchers in the Netherlands, they use this screw reinforcement. So basically, they are using the same idea, mechanically increase the interfacial performance. And this photo shows the pull-out test. They pull the screw reinforcement out from the concrete. There are some cracks after pull-out. The results are also very encouraging. In addition to the mechanical improvement, some researchers in Monash University, they are trying to put polymer in between the layers. So they put some polymer to increase the tensile strength. The direct tensile strength is measured. You can find this red color column is the direct tensile strength without anything. This is the cold joint, so the strength is very low. However, if they put some polymer, and the polymer can have interactions with the upper and lower concrete, so the tensile strength can be tripled. This is a very remarkable increase. Okay, so these are the main research efforts to increase the interlayer bond. Next, I'm going to talk about the solution. Oh, sorry, one research group In Melbourne, Swinburne University, they are trying to use cement paste to increase the interlayer strength, because cement paste is relatively cheaper and more affordable rather than polymers. So they investigate different mixed proportions of paste. So their tensile strength is tested in this way. So they directly pull the samples and see how strong the tensile strength is. And a very good result has been obtained from this research group. And many people are asking how to integrate reinforcement with the 3D concrete printing. There are a few ways. Let me first introduce the post-tensioning. 3 years ago, the Netherlands researchers have successfully printed the concrete column, a beam with hollow sections, and they used post-tension method to reinforce this 3D printed concrete beam. So they apply the steel rebar and then put some tension to the steel bar so that the concrete parts can be compressed and integrated. And this is how they did the preloading testing. Now this bridge has been in use for 2 years. I think the condition is very well now. This is the post-tensioning and from the Netherlands. And some research groups manually put the steel mesh or steel bar during the printing. So the previous one, this is after printing. And this one, they are using, they're adding steel mesh or rebar during the printing. So after they print one layer, they will put some steel mesh or steel bar manually. So the shear strength can be obviously improved. And some research groups in Western Australia University and the TU Indohof, they try to integrate a microfiber during the printing. So they don't do manually, they just integrate the fiber during the printing. So whenever the concrete is printed, the fiber can be integrated in the layer. So the layer is automatically reinforced. So the ductility is much improved based on their findings. And then another method is combination of traditional concrete casting with 3D concrete printing. They use 3D printing to produce the formwork, and then in the hollow sections of the printed product, they insert the steel gauge and then pour in fresh concrete. So they will use, this hybrid method to build multi-story buildings. And the industry, these two methods, these two photos were the method adopted by Chinese and a Russian company. This is the construction site in the Middle East. Okay, so another challenge is how to include coarse aggregate in the printable concrete. This is extremely challenging because the coarse aggregate will reduce the flowability, will reduce the rheology a lot. And last year, one Chinese company, they invented this gantry type 3D printer. They mentioned that they can print a ready-mix concrete. From the figure on the right, you can see that they can include coarse aggregate in the mixtures of the concrete, and then they put it into the printer head, and then they can print a power station. You can see the dimension is quite huge. But one thing I need to highlight here is that if you observe carefully, I circle it to highlight that in this printer, they don't have the pumping, So they discharge the concrete and then directly put the concrete into the printer head. Then they can print it, the fresh concrete. That is the key thing why they can 3D print the ready-mix concrete. Otherwise, if the 3D printing is connected with the pumping, it's very hard. It's still very challenging. Okay, here I want to introduce my work. This is done by my PhD student, Mr. Yu Shiwei in Melbourne. We introduced the aggregate bed 3D concrete printing. We extrude paste onto aggregate bed. Okay, so we extrude one layer of cement paste or mortar. Then we spread one layer of coarse aggregate. So the aggregate can be bound by the by the cement paste. Then we put another layer of cement paste. Then the cement paste could diffuse into the pores to fill all the voids in the aggregates. Then we put another layer of aggregate. Then we repeat this step and step. Then finally we can produce our concrete products. And later I will have one short video to show you the main steps. And this is the 3D printer we used. Basically, this is a gantry type 3D printer, and the cement paste or mortar is put into this black color paste feeder. And the cement paste will be injected or extruded from this printing head. And everything will be controlled by the computer. So we designed the model, and then we gave the printer the order to print according to our print path. So here is one short video to illustrate how it works. So this is the aggregate bed in the box, and we print a cement paste layer so the cement paste can diffuse into the aggregate. Then we spread aggregate on top of the cement paste. Then the aggregate could be bounded by the cement paste at the bottom. Then we spread the coarse aggregate. Then we print the second layer. And then we repeat the spreading, the spread of the coarse aggregate and the printing. So we keep repeating these procedures until we realize the product we have designed. So we leave everything in the box for 24 hours. Then on the next day, we remove everything. And the product is here. And the unbounded aggregate can be recycled. So this is the final product. You can see the coarse aggregate can be successfully integrated during the printing process. Okay, so for the final printed product, the aggregate content is about 40% compared to traditional 3D printed concrete. This is quite high already because traditionally there's no aggregate at all. Another good thing is the unbounded aggregate can be reused. So basically we are not wasting any materials. So my PhD student is currently working on the materials optimization and numerical modeling, and as well as the automation of the aggregate spreading. If you have interest, please download this paper through this link. This was newly published, so it's free to download. Okay, the last challenge to 3D concrete printing in the talk today is the long-term performance. The research in this area is very limited because people just started working on 3D concrete printing. But earlier this year, one research group in Belgium, they started to look into how is the performance of the concrete in the chloride environment. So you can see the white color or the silver color is the chloride penetration depth. One thing to note is that this is the interlayer, so actually the penetration depth would be deeper at the interlayer place. I think this is strongly linked with the pore structure. This is one field sample from the printed concrete from a Japanese research group. You will find that there are lots of voids in the concrete after printing. This is due to the printing process, unavoidable or very hard to avoid. So one of my PhD students, he is trying to link the long-term performance with the internal structures. This is this CT scanning at the bottom, particularly the figure B. It shows the very unique pore structure or the void distribution in the 3D printed concrete. The pore is it has a very strong direction dependent distribution. This is along the printing direction. So any moisture, chloride, carbon dioxide can mitigate.
Seems that Hongjian's voice is lost.
Yeah. Hongjian, we cannot hear you. Can you unmute? Okay, I unmute you already.
Can you hear me now?
Yes. Just
Oh,
now you mute yourself
Oh,
accidentally.
really? I'm sorry. Maybe I.
In your last
the
slide, from your last slide, you mute yourself.
Okay. Okay. This one. Maybe I just two slides left. Okay. This one maybe. Yeah. So
Yeah.
this is the newly purchased 3D concrete printer in the Department of Civil and Environmental Engineering. And it has a dimension of 2.5 meter, 1.8 meter, and 2.6 meters. So it can basically print a good, decent structure. And this short animation shows you how it works. I have to acknowledge Ms. Deng Jinyu, a second-year undergraduate student who helped me build this animation. Very obvious to see how it works. If you want to print a hollow wall, it can be done very fast and without any foam work. In addition to the 3D printer, we also have a rotationary real meter, which is very important to design the suitable printing concrete. And there's another equipment which is called digital image correlation. This could help us to monitor the deformation during the printing or after the printing. And lastly, I would like to introduce a few standard concrete testing, high accuracy and high capacity instrument, and a carbonation chamber, rapid chloride penetration, and water penetration. This can give us the right instrument to characterize the printed product. Finally, I would like to acknowledge my students, collaborators, and sponsors. With that, I would like to end my presentation. Thank you so much for staying with me.
Okay, thank you, Dr. Tu. Just a note to the audience. If you have any question, you can go to the Q&A tab and you key in your questions. We will try to answer as much as possible, some privately and some later on. We can repeat the question and answer to the general audience if there is time. Okay, so now I'd like to invite Dr. Keng to make his presentation. Dr. Keng?
Yes. Thank you very much, Prof. Quack, for the kind introduction. My name is Guo Qing. I joined the Department of CEE in the US last year. In the next 20 minutes, I'll share with you what I think is the most important and representative scientific questions in the study of cement and concrete. So in the research community of cement and concrete are interested in a very long list of questions, starting from the hydration of cement to the fresh state of concrete mixture, to the performance of hardened concrete, to the durability of concrete, and to the sustainability of construction materials. Obviously, it's not possible for me to summarize all of them in 20 minutes. So I will give you what I think is important and what we are currently working on or we are planning to work on. So let's look at the hydration mechanism. Portland cement is the mostly widely used cement nowadays in construction practice. It's mainly composed of clinker phases such as C3S, C3A, C2S. So right now, we are not completely sure about the hydration mechanism of these phases when they mix with water. We're also looking for ways to numerically model the kinetics and the hydration rate of these phases in a precise way. We're also trying to understand more about how the porous microstructure of the hydration product develops and how it evolves with hydration time and how it influences the property, macro scale property of our concrete. For example, strength, permeability, and diffusivity. Now, to give you an example, C3S is the most important clinker phase in Portland cement. When it meets with water, it will produce CSH and CH. CSH is the most important binding material in our modern concrete. This reaction can be classified into 3 stages. And we have a very special stage here when the hydration rate of C3S is very low. And this stage gives us the time window to cast concrete, to place concrete, and to pump concrete. However, we're not completely sure what is the reason that leads to this very slow reaction rate. Okay, we also don't know what triggers the termination of this period, that hydration enters a acceleration and then a deceleration period. All of this still remains mysterious to us. In the meantime, we notice that changing the chemical composition of the cementitious system will change the morphology of the hydration product a lot. If we look at the hydration product, the CSH of the pure C3S, we see a lot of fine needles as the hydration product at about 7 hours. However, if we dope the element zinc into C3S, we end up with needle-like hydration product, but much bigger, okay, much thicker and much longer. If we have aluminium in the hydration product, the CSH growth change from this one-dimensional growth to a way of two-dimensional growth, not into needles, but into foils, into sheets, okay? So this provides us the possibility of engineering the chemistry of cementitious system so that we can control the morphology of the hydration product and further control the macro scale behavior or performance of our concrete. Now, in the meantime, we're also interested in developing new cementitious system, okay? We want to provide new binding systems. For example, over a very long time, we have accumulated a lot of experience of using supplementary cementitious material such as fly ash or GGBS. And the cutting edge research is trying to push the limit of using these supplementary material as much as possible in cementitious system and to understand their benefit to the long-term durability of concrete. And in recent years, there are other very hotly studied cementitious systems, such as the limestone powder plus the calcined clay system. We call it Lc3 Cement. And also the alkaline activated materials is very popular these recent years. And also the sulfur aluminate cements with or without baelite faces, and many other new binding systems. Now, to give an example, let's look at the Lc3 system. In this Lc3 cement, we replace 50% of Portland cement clinker with calcined clay, limestone, and gypsum. Those 3 materials are conventionally considered as not reactive, okay? But we figure out that even though we replace half of the cement clinker with these non-reacting phases, we're not sacrificing the strength of cement paste too much. When the kaolinite content in the calcined clay is above 40%, we realize that the strength of the Lc3 paste is already comparable or even higher than the strength of normal Portland cement. If we look at the durability index, for example, the chloride diffusivity, we see that for Portland cement, at the age of 2 years, the penetration of chloride into the cement paste is beyond 30 millimeter. However, for this Lc3 cement, there's only a penetration depth of 10 millimeter. So this Lc3 cement is the outstanding binder that provides comparable strengths, better durability, but a much lower carbon footprint and a much lower cost. Okay. Now, moving forward to the fresh state. For the fresh state of concrete mixture, we're interested in understanding the physical origin of the yield stress of the mixture. We're also looking for ways to precisely measure them. We are also trying to understand more of how the chemical admixture interact with cement particles, and how does that affect the workability of our cement. And we're also trying to model the shear behavior of concrete mixture in a more precise way. For example, for the fresh cement mixture, we already know that the rheology behavior of the fresh mixture is a result of the competition between the Brownian motion of the cement particles, which is the random motion of cement particles in water, and the colloidal attraction between the particles and the buoyancy of the particles in water. If the Brownian motion dominates, we see that the suspension will not have any yield stress. That means the cement particles will not touch each other. They will be away from each other. And this is exactly what we want during the casting and pumping stage. We want the cement to be extremely flowable and pumpable. If the colloidal attraction forces dominate, that means the cement particles would like to be touching each other. And then they will form a percolated network with interacting forces. And the whole matrix will have some type of strength. And this is what we want when we want the cement paste to harden faster, to set faster. If the gravity force dominates, then the cement particle will simply sink down. And this will result in a significant segregation and bleeding problem. And this is something we want to avoid. Now, moving on to the hardened state. The cement and concrete research community has been looking for ways to design products that has a specific performance for a very long time. For example, we're trying to design concrete that has high strength or ultra high strength. We want to design concrete that has a extremely high workability so that they can be self-consolidated. We also want to design concrete to have a low hydration heat or to have a low weight and many other performances. As an example, in recent years, one of the most attractive topic is to develop a ultra high performance concrete. Ultra high performance concrete usually has a compressive strength that is higher than 120 to 150 megapascal. It has an intensive dosage of fiber reinforcement, and it is able to self-consolidate. There are already some market available products. Okay, so if you look at the recipe of these products, you'll see that they all have a very high content of Portland cement. Okay, at the scale of already 1,000 kilograms per cubic meter of concrete. They all use fine sands instead of the combination of fine and coarse sands. They all have a high dosage of silica film, of steel fibers, of water reducer, and a very low usage of water. Okay, so with this recipe, we're able to generate a matrix that is very dense, that is very strong. If you look at the microscale image of conventional concrete, the interfacial region between the paste and the aggregate is usually very weak and porous, and that's the weak zone. That's the place where concrete will fail first. However, in the ultra high performance concrete, this weak interfacial zone is now completely fixed. It's very dense and strong. The addition of the fiber further enhanced the strength of our concrete and also enhance the ductility of the concrete. Using all this knowledge, we still need to figure out a better way to select and to proportion different raw materials. And we have to understand and better control the loss of workability of the UHPC so that the time window to place the concrete is longer. We're also trying to understand more the autogeneous shrinkage of this concrete, because this concrete always exhibits a strong autogeneous shrinkage. And we are also trying to develop a life cycle assessment model. With this, because UHPC is always very expensive, we have to justify that during the whole service life, this UHPC requires the least amount of maintenance, right? And then we can justify the usage of this expensive product. Now, moving on to the durability of concrete, the research community have long-term interest in a list of phenomena that cause the degradation of concrete. For example, the steel rebar corrosion, the sulfate attack, the drying, shrinkage, and creep, the carbonation, and many other phenomena. To give you an example, for steel rebar corrosion, we already know that when we place steel rebar in concrete, the surface of the steel rebar will be covered with a thin film. We call it a passive film. This film is very dense. It prevents the steel to corrode. However, if the pH value of the concrete drops, or if we have chloride penetrating into concrete, they will destroy this passive film, and they will result in an active corrosion of the steel rebar. In many standards, they define a concept called critical chloride content. That means when your concrete contains a critical amount of chloride, we will consider the rebar to be at a danger of corroding. However, different researchers have reported very different value for this critical chloride content. Some researchers says that if you have chloride content of about 0.8%, then your steel will corrode. But the others said that the critical chloride content can be as high as 2.1%. In the meantime, if we look at the degree of damage as a function of the age of the structure, we also have to understand better when the corrosion will happen. We need to know, we need to predict the onset time point of the corrosion. Also, we need to know better the mechanism of the corrosion propagation so that we can determine the right timing for fixing, okay? We do not want to fix the reinforced structure too early. We also do not want to fix it too late. And all of these will require scientific research to better determine the perfect timing of fixing. Now, the last but not the least, sustainability issue of construction material has attracted a lot of attention in the recent decades. The research community is looking for ways to use a broad type of industrial waste and also municipal waste as construction materials. And the community is also looking for low carbon cement. We already have some options, as I have introduced. We're also looking for ways to capture and utilize CO2 in our construction material. We're also looking for a better or a more meaningful life cycle assessment of a construction material solution. Now, to give you an example, in Singapore, every year, there is a large quantity of sewage sludge produced by our wastewater treatment system. These sludge are currently all incinerated to ash. We call it incinerated sewage sludge ash, ISSA, and these ash are completely disposed by landfilling, okay, in a Samarco landfill. Every year, the amount of this type of ash is at the scale of 30,000 tons, okay? And we are looking for alternative ways to deal with this waste so that we consume the capacity of the Samarco landfill in a slower rate. Now, if we look at the chemical composition of this sludge ash, we see that it has a high content of silica, a high content of aluminium, and a high content of calcium, okay? And this is very comparable to fly ash, which is already a well-established supplementary cementitious material. That means this incineration ash can potentially be used as a supplementary cementitious material as well to replace cement, okay? There are already some researchers working on this. From the existing study, we see that some researchers found out that adding the sewage sludge ash will significantly decrease the strength of our concrete. But some found out that the decreasing is very negligible, okay? There's a decrease of about only 10% of the strength if we replace 20% of cement with this large ash. And there are researchers showing that simply by grinding this ash, we will significantly increase its reactivity, okay? So there is a lot of work to be done to facilitate the usage of the incineration sewage sludge ash as a supplementary cementitious material in Singapore. We should monitor the physical and chemical nature of our local incineration sewage sludge ash over a long period of time. We need to explore proper treatment methods to enhance the reactivity and ideally also to recover the phosphorus inside the ash, because this is a valuable fertilizer material. We also look for better performance tests to track the workability, the strength, the durability, and also the leaching of hazardous contents from the sewage sludge ash over long term. And lastly, we're also looking for product developments. We want to develop concrete products using this ash that satisfy the local standard specifications and also meet the demand of our industrial partners. So why we need to answer all these questions? In the new era of climate change, there is a worldwide trend to develop cement and concrete industry into a circular economy, okay? And this provides both challenges and chances for Singapore. In Singapore, we don't have that many natural resources, so we want to provide more options. We want to develop new concrete recipes using new cementitious material, using new aggregates. Also, Singapore is a world pioneer in novel construction practice, such as PPVC, prefabricated, precast volumetric construction. Okay, so this requires the concrete to be very workable. So we have to enhance the performance of our concrete to satisfy this construction practice. In the meantime, Singapore, as a tropic country, it has a warm, wet, and marine condition, okay? And this is the most unwanted condition for rebar corrosion. So we have to monitor the long-term behavior, long-term fate of our reinforced concrete infrastructure in Singapore. And lastly, Singapore has a high standard for the environmental target. That means concrete industry should contribute to the recycle, the reusage of industrial wastes and also municipal waste. Now, all these questions are actively being studied in our concrete research teams in NUS, Civil Engineering of NUS. We have three faculties, Dr. Bang Zidai, Dr. Du Hongjian, and me. We are actively working with the cement chemistry study, developing new types of cementitious materials. We also have a very long list of senior researchers who are very active in developing new concrete products, in developing new reinforced structures. We have a large center for advanced for advanced materials and structures study. And we also have a world-class laboratory for structure engineering. In our laboratory, we have a good collection of facilities such as XRD, calorimetry, thermogravimetric analyzer for the study of cement hydration and the microstructure evolution. We also have access to electron microscope, NMR spectroscopy, particle size analyzer, ICP, zeta potential analyzer. All of these equipment allow us to look at the evolution of cementitious system right from the second of mixing until the very end of the service life. On the application side, we also have a set of mechanical testing facilities from small scale to large scale. We also have environmental chambers that allow us to control the relative humidity, the sunlight exposure, temperature, CO2 condition for acceleration test of concrete under different environment. We're also able to track the volumetric stability by doing shrinkage test and creep test over long term. So to close my presentation, our mission is to advance the science of cement and concrete research, as well as to serve the local practice. We're happy to take questions And you can also email your questions to us. Thank you very much.
Okay, thank you, Dr. Geng. Actually, quite a lot of you already posted questions under the Q&A tab, and some have been answered, and there are new ones coming in. And I think I let Tu Hongjian answer Kueh Kwan first. How is concrete used in 3D printing tested for strength and durability? Like what are done for concrete use for construction now? Then
Okay.
after that, then I let Dr. Geng answer all the other questions that is related to his talk. Okay? Then, yes.
Okay, Prof. Greg. So for the question raised by Mr. Lim, actually the concrete testing method is not standardized yet. So what we are doing in the research community is that we just use the traditional or the normal concrete testing method to characterize the compressive strength, the fracture strength, pore structures as well. So regarding the structural application or durability, durability also for the chloride penetration, we have to make the printed sample into the standard form, like for example, a cylindrical disc for the rapid chloride penetration. So there's no standard testing yet method for this new technique.
Okay, can I check with the audience whether y'all can see the questions or not? I assume that you can see the question, then that's where I thought that you read the question, then the presenter will answer. So maybe now I would like to invite Dr. Geng to answer some of the questions. For example, Tan Tuan Ho, the first one.
Yeah, okay. So now I'm reading the first question. It's a very good question. Are there any research in concrete replacement materials involving locally available materials instead of GGBS, fly ash, that unfortunately is also imported? This is important in improving the sustainability and resilience of our local construction industry. This is a very good question. In fact, in Singapore, there are also some supplementary cementitious materials to be explored. For example, in our department, Dr. Banzidai, and I think also Dr. Du Hongjian has the experience of working with a local marine soft clay. Hongjian, if you want to add up on this.
Oh, thank you, Guoqing. Yes, I think Prof. Banzidai and I have been working on the use of marine clay, but we need to simply thermal treat it, then we can use it to replace cement up to 30%. Thank you.
Okay. And also, I have the interest of using the incinerated sewage sludge ash and also municipal waste. Okay, using this ash as supplementary cementitious material as well. In Singapore, we don't have the large-scale industry to produce GGBS or fly ash, unfortunately. For the second question from Kim, Mr. Kim, great for green approach. Can UHPC uses manufactured sand for grain be very lightweight for easy lifting? Well, as far as I understand, the UHPC application has already, the technology has already engaged the lightweight sand. So the quality of the sand does not need to be extremely well. In our department, Prof. Richard Liu has worked with UHPC using lightweight sand already. Okay, we can talk with more details later on through email. Yeah.
Jane Lim, the one by Jane Lim. Out of curiosity, is there any reason why there are rebars used in the Singapore uncoated?
Okay, I'm not an expert for this question, but I can share with you some of my experience. Coating rebar this practice is actually not particularly popular, also in some other places. The normal epoxy coating of rebar is found to be, in real practice, in the handling of the rebar, coated rebar, it's very easy to create defects on the surface of rebar. If there's one defect on the rebar is very vulnerable to corrosion as well, because the other coated region would not contribute too much to the to preventing the corrosion. The defected coating will already generate a very strong corrosion. So coated rebar, using coated rebar has to be taken great care in the real practice. So another question from
anonymous, yeah.
There's one. Oh, this is 3D printing. Sorry. The next question is, how willing is the industry to adopt new materials which potentially are more expensive? Okay, I would say this is rather a question for our industrial partners. In Singapore, we have local standards, and all the products, concrete products, has to follow the standard specifications. As far as I can feel, the industry is very interested, including the government agencies. They are very interested in exploring new types of construction materials, even new binding systems. But the way to move from laboratory exploration to a real practice is still very long, I would say.
I think I let Prof. Tam add the answer. Prof. Tam, you are very experienced with the industry. So would you like to answer this question?
Okay, right. I'd like to mention that one of the problems with the epoxy bonded bar is what we have any local defect, then you become actually worse. Then you get very deep localized corrosion. And it's very difficult to avoid damage. Even when you vibrate, the coarse aggregate can hit the coating. And if it scratches it, and then if it reaches the bar, then you become a local defect. So in effect, if I'm not wrong, some years back, the practitioners challenged the epoxy bonded bar manufacturers to say, come and look at some of our epoxy bonded bar structures that are corroding. What are we going to do? So I understand today they are having double layers. They even have another layer inside, zinc, to act as sacrificial, so that any local defect will be covered by the zinc layer before the epoxy outside. So there are improvements in that direction, but they are very expensive. And when you start to bend bars, then you have to repair all the bends. So these are some of the practical problems.
Okay, Prof. Tam, there's the next question there, that is, how willing is the industry to adopt new materials which potentially are more expensive? So maybe with your many years of experience to see new things coming in, you can project into the future.
I think this has to be based not on cost effectiveness. You have to look at the environmental issues. If you look at cost effectiveness, then anything that's more expensive, the user will say, what for? And also because the way we work, the maintenance is the owner, not the developer. So developers will not bother to go into more expensive material that may last longer and affect their sales compared to the competitor who does not. And not every purchaser is knowledgeable enough to know value for money. And that is the biggest problem with new material, how to prove that it's worth the money.
Yeah, okay, there's one for you from Ho Tian Sing. He's asking you about the viscosity meter.
There are actually viscosity meters that are available in the market, but it is not something that is so easy to use. It's mainly used for developing self-compacting concrete. So unless you do a lot of self-compacting concrete work with different requirements and so on, you would not purchase this expensive equipment just not being used. So I think it is a problem of lack of demand for special SCC, that they do not need to do a lot of development work. They are available, commercial. We had, NUS had one very old original model that one of our PhD students did for self-compacting concrete. But that type of model is out of demand now. Now they got much better models. If anybody is interested, I can help them source for one.
Okay, there's a last question for Dr. Geng. Dr. Geng, you want to answer that one?
Is there any facilities available around the world to produce granite fines? Well, to be honest, I'm not an expert on this question. So by granite fines, do you mean something like the quarry dust, the dust product from,
Yes.
The research on using quarry dust is actually quite active. People are using it as fine aggregates, okay, to replace sands, and also as fillers. These extremely fine granite particles, they can be used as to provide a seeding effect for cementitious material, for the cement hydration product to form. It will have a significant improvement to the early hydration rate and strength development of the hydration product. As far as I know, I don't know if there's any company that specifically producing this for commercial use. This is something I'm not very aware of.
Yeah. Okay, so I think it's a good time to stop now because we answer all the questions and time now is about 5:37. So I'd like first to thank all the speakers for sharing their knowledge with us, and also like to thank all the participants for making effort to attend and asking very interesting questions. And I hope to see you at the next webinar. So thank you very much.
Thank you very much.